Any questions?
Şimdi elektrostatik için şey dedik. Scalar potential continuous. Magnetostatik için de vektör olarak.
Vector potential is always continuous. You see, it's important that you understand why it should be continuous rather than memorizing that it is continuous. You see, we know that this property, B is equal to curl of A, which tells me that if I take the A, integrate over a closed loop, this is equal to B integrated over the surface. I'm just integrating both sides over the same surface, but since this is the curl of a vector field integrated over a surface, I can always write it as the integral over the boundary of the surface. But this is what we call the magnetic flux. This is how we define it. Now, you see, if you have any boundary, and you just take this loop, around this loop, A dot dl, when you take the limit as d goes to 0, this just becomes A outside minus A inside. Dot dl vector. This one is, let's say, dl vector. And but you see, as the flux, magnetic flux, is just the B field times the area. When you take the limit d goes to 0, the area goes to 0. So unless B is infinite, if you have a region where B might be infinite, in that case, unless B is infinite, phi goes to 0 in that limit. But if phi goes to 0, it just means that this should be equal to phi, that should be 0. So this tells me that the component of the vector potential parallel to the surface is continuous, not the perpendicular component. No, this phi is the flux. This only tells me that the component parallel to my surface is continuous. In order to claim that A is continuous, I also have to show that the perpendicular component is continuous. To show that the perpendicular component is continuous, we know that the divergence of A is equal to 0 in our choice. We made a choice in defining our vector potential. We chose the vector and since there are infinitely many vector potentials, we chose the one whose divergence is 0. And using this law, we assume such a surface. So since divergence of A is 0, if you integrate A over any closed surface, then the integral is 0. It's just like the divergence of B is equal to 0. If divergence of A is equal to 0, then its integral over a closed surface is 0. But this tells me that, again, just take over this cylinder, A dot ds is nothing but A outside minus A inside dot n times, let's say, S. This is my ds. This should be equal to 0. So this tells me that the component of A in the direction of n is also continuous. From the previous expression, I know that the component of A horizontal to the surface is continuous. Now this shows me that the component of A perpendicular to the surface is continuous, and hence A is continuous. So it's crucial that you should be able to derive these boundary conditions. Given the curl of a vector field, can you conclude that its horizontal or perpendicular components are continuous or discontinuous? Given the divergence, what can you say about how it changes as you cross a boundary? You should be able to derive them, not just memorize them. Now let's go back to our vector potential. A at the point R, we had seen that it can be written in this form. And we made several applications of this. If there is a volume current density, this is the expression. If we have the line charge, then line current this is our expression, the simplified version of the same expression, basically. Now, before continuing, there will be a couple of properties of the current J that I will use. So we know the continuity equation. This just states that whether you are looking on statics or dynamic properties, this is just a statement that the total charge should be conserved. Now, in statics, statics just means that nothing changes in time, so the time derivative of the charge density should be 0. So the divergence of J is equal to 0. This just tells me that del I, Ji, this is equal to 0 in terms of the components. Now let me look at this thing. The divergence of xi times j. I just take my j, multiply it with x, y, or z, depends on what your I is. This is a vector field. I just take its divergence. Well, from the definition of the divergence, this is equal to derivative with respect to xj of xi jj which will be equal to derivative of xi with respect to derivative of xj of jj plus xi times derivative with respect to xj of jj. Now let's look at the second term first. This derivative of jj with respect to xj is nothing but the divergence of j, but this is 0. So the second term is 0. Now let's look at the first term. Well, that derivative, if I is equal to j, it's like I'm taking the x derivative of x, or the y derivative of y, or the z derivative of z, it's just 1. If I is different than j, it's like I'm taking the x derivative of y. They are different components, so it's 0. So that is nothing but Kronecker delta ij. And keep in mind that I'm summing over j. So when I make that summation, divergence of xij, this is equal to ji. This is one property of j that I will be using. Now let me show another property of j. Let's look at this integral. xijj. I'm taking one component of the position vector, another component of the current density, and I'm integrating over all my volume. This is equal to xi times the divergence of xjj, sorry. I just show that instead of jj, I can just write it as I multiply xj by my current density and take the divergence. It's this property over there. Integrated over the whole volume. Now I will do an integration by parts. Okay, so let me write it in this form. xi del over del xk of xj times j d cubed v. This is equal to del over del xk of xi xjj minus xjj, no, this is jk, sorry. xjjk, derivative of xi with respect to xk, d cubed v. Well, you see, if you just take this derivative, just consider this term as the product of xi and this one. If you take the derivative, it's just the first one multiplied by the derivative of the second factor. It is the term I want. There is the additional term, the derivative of the first one multiplied by the second factor, which doesn't appear on the left-hand side, so I subtract it. But now you see, you have a total derivative integrated, but the derivative or integral of a total derivative just gives its values on your boundaries. So since we are looking at the volume integral, the first term just becomes a surface integral. So the first term is actually xi xj j dot ds. Well, basically, this first derivative is nothing but the gradient divergence of this one. Let me write that step also. The first derivative is the divergence of this thing integrated over my volume minus xj jk. That derivative is Kronecker delta ik. Well, the volume integral of a divergence, I can always convert it to a surface integral. My surface is at infinity. There is no current on my surface, so this term is 0. I'm left with that term. And that term, when I sum over the k's, it is minus xj ji. Which basically tells me that if I take one coordinate, multiply it with one component of the position, multiply it with some other component of the current, if I change the components, ij, ji, the integral just takes a minus sign. Just one property of the current density, which basically follows from the fact that its divergence is 0. Now, this is another property that I will be using. That's why I derived it now. Now, our vector potential. mu0 over 4 pi integral of j r prime divided by r minus r prime d cubed r, or dv. Now, if you remember what we did in electrostatics in our multipole expansion, well, we can basically do the same thing over here. And the multipole expansion was, we have a local region where the j is non-zero. This is my origin. I am looking at the vector potential at this point r. Let's say the size of this region is of the order of d. So this tells me that 1 over r minus r prime, you see r is very large, r prime is very small compared to r. So this I can expand as 1 over r sum over r prime to the L over r to the L PL of cosine theta. This is my r prime. This is the angle theta. Or let me just call it theta prime. So this was what we had done in, or we can also write it as, let's say, 1 over r plus r dot r prime over r cubed plus higher order terms. And in fact, if you remember in electrostatics, this was our monopole term, this was our dipole term. We have the quadrupole, octupole, etc. But here I will be concentrating on this dipole only. So my vector potential, if I use this expansion, which was, remember, integral of j of r prime divided by r minus r prime dv prime. This is equal to 1 over r of j of r prime dv prime plus j of r prime 1 over r cubed j of r prime r dot r prime dv prime plus all the other terms. Now let's look at the first term. Let me look at ji of r prime dv prime. I'm just taking the I component of this first integral. That is my magnetic monopole term in my multipole expansion. And this is equal to divergence of xi times j, xi prime j of r prime dv prime. This time the derivatives are with respect to the primed coordinates. This is the property that I had proven just before. This derivation. You just take the derivative. This is my divergence. The definition of the divergence is you have this vector field, take the j component of your vector field, which is xijj, take its derivative with respect to xj. Then I just carried out these derivatives, the derivative of the first term times the second one, plus the first term times the derivative of the second term. Well, the derivative of the second term, or the jj, the derivative of jj with respect to xj, when I summed over j's, it just gives me the divergence of j, which tells me that in magnetostatics that is 0 because of the conservation of electric charge. And then if you look at this term, the derivative of xi with respect to xj is 0 if I and j are different. It is 1 if I and j are the same. And so this derivative is nothing but my Kronecker delta, and I'm summing over jj. I'm summing over j. But this Kronecker delta just tells me that in the sum over j, only the term j is equal to I term survives, and the j is equal to I term is the I component of j. So if we are looking for the I component of the current, I can always write it as some kind of a divergence. That is what I'm using in the next steps. So I'm here. I made my multipole expansion. Now I'm looking at this term over here. But this term, I'm looking at this a vector. I'm multiplying a vector with a number, summing over all my points in my region. I look at the I component. Well, the I component of that vector is the integral of ji. But ji I can write as the divergence of some vector field. But if it's the divergence of some vector field integrated over a volume, this is nothing but the surface integral. But on my surface, there is no current. My surface is basically at infinity, and I started by assuming that J is just localized over here. There's no current outside. So this term is 0. Well, in my electrostatics, this was the monopole term. Well, this basically just repeats our claim that in magnetostatics, there are no magnetic monopoles. In fact, in electrodynamics, there are no magnetic monopoles. The monopole charge of a given current density is also always 0. There are no monopoles. The first term is the dipole. The first term in my expansion is the dipole term. Now let's study that dipole. So A of R is equal to, sorry, here I forgot a mu 0 over 4 pi. mu 0 over 4 pi 1 over r cubed, the integral of j evaluated at the point r prime multiplied with r dot r prime, integrated over r prime. Now what I would like to do here is take this r out of the integral. It's independent of r prime. I can take it out of my integral, but I also would like to just write the remaining part in a simpler form. That's what I will be aiming at. Now let me look at this vector product. Because if I somehow can write this expression in terms of such a vector product, well, or I can easily take it out of my integral. That would be nice. So this will be equal to j of r prime multiplied with r dot r prime minus r prime j of r prime dot r. Now the first term is nice. That is the one I was looking for. But I also have this second term, which I need to simplify somehow. Or if it is 0, show it to be 0, etc. Now, just keep in mind these expressions appear in a volume integral. Let me look at the last volume integral. Let me take the I component. This is equal to integral over the volume xi prime xj jj evaluated at r prime. Now I can take that xj because it's independent of the coordinates of r prime. Xj xi prime jj of r prime. But now I can use the identity that I just showed in the previous slide. If I exchange these indices inside my integral, I get a minus sign. So this is equal to minus xj dv prime xj prime ji. So this tells me that this is equal to minus, let me just write it as a vector, r dot r prime j r prime, the I component. You see, we started with this expression over here. I looked at that expression, the I component, and we had just shown that it is equal to the first term on that equality with a minus sign. And which kind of tells me that this integral over here this one is equal to twice j of r prime r dot r prime dv prime, or j at the point r prime r dot r prime dv prime. This is equal to 1 over 2, or r cross 1 over 2 integral dv prime j of r prime cross r prime. Now let's go back to our A. This was our A. Now we had just shown that this is equal to mu 0 over 4 pi 1 over r cubed r cross 1 over 2 dv prime j of r prime cross r prime.
Hocam şu R vektörünü nasıl integral edeceğim?
This one. You mean from here to here?
İntegralin dışına nasıl çıkıyor?
You see, I'm integrated over the coordinates of r prime. This is just a constant with respect to r prime vector. It doesn't depend on the coordinates of r prime vector. So that's why I can take this out of the r prime integration. And when I do that, this is what I obtain. And this is what we call the magnetic dipole moment. Before we had the electric dipole moment, if we expand the electric potential of an arbitrary localized charge distribution, we had seen that there is the monopole term plus the first term is the dipole moment term, which changes as in the potential as 1 over r squared. Now we do the same thing for the vector potential. For the magnetic fields, there is no magnetic monopole term. So the first term is the magnetic dipole. And the magnetic dipole, again, just goes as this 1 over r squared, has this 1 over r squared behavior. Well, let's see. Let's go back to our the exercise we did in the first hour. This is what we had over there. There's a sign problem somewhere. But you see, here I have the m cross r. Again, this is, well, r cross m and m cross r, they just differ by a sign. Here there should be a minus sign somewhere, which I seem to have missed. Or, sorry. No, there's no, you're right. This is m cross r, and this is r prime cross j. Well, you see, in my derivation, I have the j cross r prime. So if I change their places, I get one minus sign. But here I get r cross this integral. I also change their position. That gives another minus sign, so there is no minus sign change over here. Okay, so this is the correct expression. So basically, our rotating sphere was a system which has the magnetic dipole moment that we had studied before. It doesn't have any other multiples. You see, in this expansion of the A field, there are many other terms which we neglected. In this rotation top, it's an ideal dipole, magnetic dipole. There's no other terms. We didn't make any assumptions in that derivation. So, constant with respect to what? You see, this only depends on my current density. Once you know your current density, the m is this integral, so which doesn't depend on this r prime, it doesn't depend on your observation point, for example. Whether you are making an observation at this point or at that point, you have the same magnetic dipole moment.
Ama oradaki dipole moment constant birinci soruda.
This is also constant in the same sense. It doesn't depend on your observation point.
Hocam, şimdi hani böyle bir çember düşünsek, içinden de bir akım geçse, hani onun dipol geçişi demiştik ya, i çarpı pi r kare diye değil mesela. Ama burada şimdi 1/2 diye bir şey geldi.
So this is our magnetic dipole moment for this system also. Well, here I don't have a volume charge density. I only have a current carrying wire. So I can rewrite this as, well, here I have a 1/2. So there's no this mu0/4 pi. This is equal to 1/2 r prime cross I times dl. I/2 r prime cross dl. Well, let's see, this is our origin. Let's just take this dl over here. This is my r prime vector. So let's see, let me just plot it over here, just a bit rotated. This is my r prime vector. This is dl vector. Let's call this angle theta. What is r prime cross dl? Magnitude. What's the magnitude? It's just magnitude of r prime, magnitude of dl, multiplied with sine of pi minus theta, or r prime dl sine theta. Now let me consider this triangle over here. Here I have an area. Let's call it dA. What is dA? 1/2 r prime dl times sine theta. Basically because this dl times sine theta gives me the height. But you see, just compare this one and that one. dA is just 1/2 magnitude of r prime cross dl. So let's say m is equal to I times dA vector. Now, if my loop is on a plane, it's a planar loop, then this is equal to I times dA times n being the normal direction, perpendicular direction to my area. Well, if my loop is planar, in that case, n is a constant vector. It always points in the same direction. So I can take it out. So what remains is the area. This is I times A times in the n direction. Now, this A is the area bounded by the loop. Now, this is just a special case of the magnetic dipole moment. If you just have a line wire a current running through a closed loop, and this loop lies on a plane, then the magnetic dipole moment is the current times the area bounded by the plane, and the direction is given by the right-hand rule, in the sense that just curl your fingers in the direction of the current, your thumb points in the direction of the magnetic dipole moment. But if you don't have such a planar current carrying wire, it can have some arbitrary shape, it might have some volume, not necessarily an infinitely thin wire. This is the general expression we have with the 1/2 factor. Well, this result will be important for us also when, for example, we will be studying the magnetic field in matter. So we will basically treat matter as a system of magnetic dipoles, which will create an additional B field. Just like in electrostatics, what we did for to study electrostatics in matter, we put some charges in the system which created an electric field, but this electric field induced dipoles in our system, which created an additional electric field. Well, we will basically do the same thing here. We will put a current in our system, and if our system is in medium, then the medium will be magnetized. In the case of electrostatics, we had this polarization, which was the dipole moment per unit volume. Here we will define the magnetization as the magnetic dipole moment per unit volume. System will become magnetized, and it will create its own B field. Of course. You see, we are kind of 2 weeks behind the schedule. Now, I don't think we will be able to complete everything. Well, I don't really care completing, but I would still not, let's say, waste time in the sense that, okay, we will solve examples, but I will continue. So there's no recitation tomorrow. There was no request except on the 2. And so see you on Friday. I will send you an email about the final situation of the midterm.